So in this lesson we will look at the that allowances and the mold cavity layout. We will look at allowances and mold cavity layout, various allowances which are used, and we will look at the scientific rationale for applying those allowances. So we will look at first draft, a bit of fillets, we will look at shrinkage allowance, then machining allowance, distortion allowance, and all those others. Okay, and last part of this lesson is about how do you lay the cavities. Can you pack the more cavities? Can you put the cavities far apart? What are the pros and cons of that? How do you optimize the cavity layout? Essentially gaps between the cavities. So we look at that again from scientific backgrounds. Again, so starting from an example of how the tooling looks like. So little more complicated tool where we have the cope and drag pattern, and on the bottom half you have a complicated core. So in that core box you make the sand core and place the sand core in that to create the hole in this. So I'm just showing examples of industrial toolings designed by different companies. Okay, now we look at, in a simple picture, first we look at all the steps involved in tooling design. The very first step is, if you have any drilled holes in the part, you're going to drill the holes after the casting is made. You're not going to make the holes by coring, so you first remove the drilled holes. That's the first step, because many times foundries get the part drawing from the OEMs, but those are actually machined part drawings. So what first headache that they have to worry about is remove some of the holes. If only those drawings can be without drilled holes, I think foundries can save a big step in the beginning itself. Okay. Then wherever you have through holes, you add a core in that, the way we have talked about in the last lesson. Okay. Next step, the pattern in this case, or a reverse of mold cavity in this case. Okay. You combine the core and the print. So if you do a union of the part design with the core design, you get a starting point of pattern design, or the mold cavity design in case of metal die, right? So you see the top and bottom are the prints of the cores, and then you also apply draft at the parting line. We'll look at details of how to apply draft in a minute, but first look at the overall steps. Next, what we do is, if you want to machine some surfaces, you add a machining allowance in those surfaces. So you are increasing the part size and the mold cavity size. Next, the metal is going to contract at solid state, so you are going to increase the dimensions. Again, not necessarily uniform. We'll see how to increase the dimensions for the contraction allowance. And finally, the casting may distort. Okay, maybe the core will swell, or the reverse. So you are going to do the distortion allowance in the reverse direction. So after distortion, it comes to the shape which you want. So now let's look at these steps in a little more detail. Okay. First step is draft. Okay. Now you apply draft on all the faces which are parallel to your draw direction. Okay. Now if you see the table as well as the slide here, if a face is short and a close to parting line, you don't need to apply much draft, because it's very easy to remove that face from the mold. You just pull a little bit, the face is clear. You don't need much draft on that. But supposing some face is far from the parting line, okay, it's like your leveraging principle. You have to leverage far more movement to be able to pull a face which is far from the parting line. Okay, so that is you need to add more draft on a face which is far from the parting line. So if you see from the top table also, if the face height is small, or even you can say distance is also partly responsible there, you have more draft coming up there. What about an internal face? You have two faces on the top, one is external, one is internal. The internal face requires much more draft. Why? Because when you pack the sand in the sand mold, or even die casting, when the part grips the die because it is contracting around the die, you need much more force and much more leverage to be able to pull an internal face out. So any internal face will always have typically 50% to almost 100% more draft than a face in the same location, an external face in the same location. Okay, so you can see that your and these table values are for a metal pattern in an automated molding machine. The moment you have wooden pattern and a manual molding, you need almost double the values of the drafts here. Okay, clear? Draft is clear. Now fillets. You need to apply fillets for two things. One is in sand casting, you want to pack the sand around sharp corners, and the metal when it flows inside the mold, you want metal to flow smoothly around corners. So which corners are more critical, external or internal? From part point of view, internal corners. These internal corners become external corners in a mold. So external corners in a mold or internal corners in a part, you need to apply more generous fillets. But this leads to another complication which we'll see later. The more generous fillet you put, the more you'll find it becomes a hot spot there. But we will worry about that later and see how to fix that. But first, we need it to make sure the metal fills more smoothly. Next, machining allowance. Wherever you have to machine a part, wherever you are mating parts, okay, or you have to finish the part, you have to apply machining allowance because you have extra material which you are going to machine it out. Okay, depends on your what kind of metal is that, what kind of your size of the part is. The larger the part, usually the more deviation can happen, so you give more machining allowance. But that is logical. What about top and bottom face? People in industry know that by default, in the same casting, if you have to machine the top face as well as the bottom face, the top faces require more machining allowance. Slag will float up. So all the sand and slag which are lighter than the metal, in case of ferrous metals, they float to the top. So if you machine only 1 millimeter, you see a lot of dirt on the top. So you want to machine more to remove all those things. So a top face will always require more machining allowance. So you know that from what you have seen in yesterday's slides, aluminum or steel, okay, you know aluminum we said 1.3, steel we said 2.4 is your contraction allowance. But that is only for a face which is unhindered face. The moment you have, if you see on the top, the moment you have an internal pocket, you do not have to apply that much machining, that much of contraction allowance. Why? Because it will not allow that internal shape to contract. So you don't have to worry about it too much. But if a shape which is free to contract, there we have to apply contraction allowance because otherwise you will get a smaller shape.
Will the contraction vary upon the type of the core? I mean the
Yes. So if you have rigid sand, okay. In fact, if it's a they have tried in concrete molds or concrete dies, or if a metal die, okay, you don't have to apply any allowance at all. But if you have a very soft core, oil bonded cores and all that, it gives away a little more. So you can apply maybe half. So finally, end of the day, there is no going away from making some small experiments in your own foundry with your own metal process and mold metal combinations, and find out simple values of that. But these are good starting values to look at, and you can get fairly close to your final dimensions. So pockets require less contraction allowance than external faces.
in case we are using cores on the sides,
Mm-hmm.
so the package is totally made of core. For example, cylinder heads.
Yeah.
In that case also we need to give allowance on
Only if that core is preventing contraction. If the core is completely external and part is completely free to contract and there is no internal core, okay, like we saw for the fins casting, there the cores will never come hinder the contraction along the horizontal direction there. So you don't have to worry about. So you have to apply full allowance. I'm sorry. But if a core, this internal core going through core, going completely in and out, and it's a very rigid core, you need to apply less contraction allowance because it's not going to allow casting to contract. Okay. Now distortion allowance. We'll look at it in a little more detail, but this a starting point. A H shape opens up like that. So you make it inward to start with. So when it distorts outside, it becomes straight. That is the basic principle of distortion allowance. Now, how much should you apply? Again, this table gives you some nice guidelines. If your wall thickness is small, if you have thin wall casting, and if your H by length is more, okay, it will distort much more. Okay. A thick casting, on the other hand, if you see the 50 millimeter wall thickness, the distortion allowance is much less. So you need to worry about allowance depending on your part wall thickness and your H by L ratio. Okay. So again, I'm just showing in this example, you have to make the part inward. So when it distorts, it will become straight, and you get a good casting there. So all these allowances you apply, and you keep changing your part design to finally get the mold design, okay, and you can combine these allowances in intelligent ways. Supposing you have draft allowance on the side, and you also need to machine that side for some reason. You don't have to apply draft and machining both. You can do a little bit of compensation or optimization and apply a little less of machining allowance because draft is anyway there. And let's say fillet also is there. You can't put a fillet unless you put a machining allowance, because even a fillet changes the original part geometry, and if your OEM is very particular about that, a fillet has to be applied with a machining allowance if he is very particular about it. Okay, so you can always combine intelligently in collaboration with your part designer. So you finally got your mold pattern and the mold cavity, then you actually make the casting, then you realize that you have real process problem. There is a flash and the two parts are lifting out. Flash comes because the cope is lifting up and the part vertical dimension is now changed, which you never thought about before. I'm adding additional allowances here. In fact, this is not allowance, it's a natural automatic allowance applied by the process itself. You can't do anything about it. But then one more thing can happen, which is a two mold house can shift horizontally, giving you mismatch. And if mismatch is not within your machining allowance, you have to apply additional mismatch allowance to take care of this also. Okay, so that part now looks like this. So finally, when you apply all these direct allowances as well as indirect allowances because of the process, mismatch and the flash, it can add anywhere from 5 to 15% of the original weight. Okay, and how do you know that? You actually weigh the as cast part. You remove the gating and feeder and weigh that, and if you weigh your original part design, the difference can be as much as 10-15%. So it's essentially 10% extra weight which you're supplying to the customer who had never asked for it. Of course, the question of finally he pays you for what? He pays you for his design weight or your supplied weight. That's a negotiation. Okay, but if he says no, I'll pay for only my design weight, then you are unnecessarily supplying him 10% extra weight. So he'll say no, I don't need the weight. I have to anyway machine that. These arguments happen all the time in foundries. So if you minimize your deviation from the original part design, the better it is. We call it as geometric fidelity. Make it as high fidelity as possible. Now I'm just going to map the original design which we took in the beginning of this part, just to show you the difference between the original intention, what the designer wants, and the excess material which you are supplying to him. And as you can see, it can be easily 10-15%.
Sir, what allowances do you provide in the core? While making a core?
First is core print itself, you have to apply draft. That is because you have to place the core in the mold and remove the core and all that. Second thing is your metal around the core also continues is contracts. Okay, and then of course if the core is very rigid, contraction allowance may not be much, so you don't have to worry about much. So all you worry about is applying a generous machining allowance on the core, because remember cores can also deviate, especially if it's a cantilever core. Depending on the buoyancy force or net force, it can tilt up. So you need to apply generous machining allowance. So all you worry about in cores is apply a lot of machining allowance.
So most of the cases, for the tool designer, pattern maker designer has to select a draft angle, which is a very much critical part. So which factors one designer has to consider selecting a draft angle? Because many times machining designer doesn't mention that draft angle, but casting designer has to consider that draft angle, and many times tooling failure is also happen because of that draft angle.
Yeah. I'll give you an answer in an indirect way for this. If you look at plastics, okay, the plastics, the draft is designed by the part designer, and tool designer doesn't have to worry about it, because already it is a naturally drafted part. In castings, designers do not worry about draft, so we means as a manufacturer we apply a draft, and then designer says what is this, you change the geometry, so there is a tug of war between them. So if only the draft can be applied by designer himself, understanding the process, the starting point itself is beautiful. You don't have to worry about all those things, but you understand that. So I in a way answered the question in an indirect way.
Many of the part designs are done by the OEMs where the knowledge of foundry or particular casting design is not in existence.
Absolutely.
So it requires a simultaneous engineering between the OEM and the foundry designer while we design the casting parts.
How control over frequently doing the
Yes, a dimensional measurement of the casting itself, and I am not talking about just a quick check of the overall dimension, but also the entire thing. And I must tell you that these days we have very nice equipment available for full 3D geometry of the thing, which is like a white light scanner, laser scanners, 3D scanners. CMM is also there, but you have the scanners which are very fast. It's just white light scanner, you just scan from all different directions, you have and your software to build the entire geometry, and you can compare that with your reference geometry of the ASCAS part. Yeah, yeah, good.
Sir, there is a part design. OEM releases the part design and foundry makes the casting design. Okay, but it is observed that the part should be as per that black boundary condition. But it is observed that, see, that red part should be that is a 10 kg and that black border part is 12 kg.
Yes.
But it is observed that part comes up to 15 kg. Means it is more than the casting design. So supplier or foundry person says that there is a process variation. Means OEM person cannot consider what is the process variation is there. Means this is more than these allowances.
In one foundry at least we told them, and we said, and finally it was concluded, just by measuring the weight of your casting which comes out of the mold, even before shakeout, okay, or maybe if you want after fettling, if you want, you just measure, put a weighing machine and measure the weight of that and record it. Just by plotting the graph of that, you can start looking at some of those systematic errors in a foundry. Just a quick weight check which any foundry can implement that. Okay.
Apart from that, what can happen because of the variation in molding, the proper ramming is not there. The molding machine, I mean, it's
Yep.
not, say, if it is high pressure molding, then other time
Much more consistent.
more consistent.
Yes.
But if you go to
Manual operation, yes.
manual operation, the weight consistency is there.
Yes. So here we are looking at multi-cavity molds, and remember, by default it's good to, if you have a small casting and generally a big mold, it's good to put more cavities in the mold, so you are utilizing the sand better. Otherwise anyway you have to make the sand. Instead of putting one cavity, if you make 4 cavities, 6 cavities, your productivity in the foundry will increase. Okay. Except that, what happens when you pack too much? Okay. The first thing you have to worry about is what is the gap between the 2 cavities that is allowed. If the gap is too small, you have 2 complications. One is the mold wall itself will become so weak that the gap may break, which is of course a catastrophic kind of a thing. That is really bad. But the next thing is also equally bad, that if your cavities are too close, the area between the 2 cavities, the sand mold becomes too hot, doesn't allow the heat to transfer, and you get a hot spot which was not there before. Okay. So if you see in this example here, for example, if the one casting you have one kind of a uniform solidification in all the 4 corners. If you put 4 castings in the same mold, you see the corners close to each other now become hot spots, which were not uniform earlier. But I'll show you this in a even better way. You see this first casting is solidifying in a particular way. The moment you put the cavities too close to each other, the area which are facing each other become much more hot. The moment you increase the gap sufficiently between the 2 cavities, it goes back to original normal solidification pattern. The big question now is how much is too much and how much is ideal. Okay. For that we did some experiments. What we did was, if you look at the top part, we put thermocouples in the mold. So all those 1, 2, 3, 4, 5 are the thermocouples. 1 and 2 are inside the casting. 3 is just in the mold, just close to the casting, and 4 and 5 are little away from the casting wall. Okay, and the distance are given. So 3 is at the interface. Thermocouple 4 is 20 millimeters away from the casting, and 5 is 30 millimeters away from the casting. And thermocouples we are capturing the cooling curves. So if you see the cooling curves, 3 is at the interface, so 3 is really hot. We expect it to be hot, right? But 4, if you see, at a distance of after about, let's say, about 100 seconds, okay, if you look at temperature fall, the 5 after some time is almost coming down to horizontal. Okay, the 4 is still hot initially, but 5 is not affected that much. So by doing experiments like that, we are now deriving equations for how much should be the gap. So if you see in this example, if you have a solid casting or a a solid casting, okay, cylinder or a cube or a block without any inside cores, there the gap, minimum gap between two cavities should be at least equal to half the part dimension. So if you have 10 centimeter cube or a 10 centimeter diameter cylinder, distance between the two should be at least equal to 5 centimeters. Preferably 10 centimeters, but at least 5 centimeters. Below 5 you start getting serious reduction in heat transfer. That is for solid shapes. So that is not really common. Most of the castings have some cores inside, some holes inside. The moment you have, and thick walls and thin walls and so on. So if you have two cavities or two castings facing each other with thick walls neighboring each other, the minimum distance between those two castings should be equal to about twice the wall thickness. So if you have, let us say again same 10 centimeter casting, but now the wall thickness is only let's say 4 centimeters, then the minimum distance between two castings of 4 centimeter wall thickness should be equal to 8 centimeters. Or if you have a 2 centimeter wall thickness, the minimum gap should be equal to 4 centimeters, twice the wall thickness in the neighboring area. The casting may have different wall thicknesses. You have to worry about wall thickness which is facing each other. This is from our simulation and experiments we found that. So you can use this as a starting guideline for deciding the gaps. So how do you really decide the best combination of mold size and number of cavities? You have two parameters here. You may have 3 different mold boxes in a foundry, and a particular mold box can take either 1 or 2 or 4 or 6 cavities. So which combination is best? Okay, how do you decide that? You take each box, you take the box number 1, and then you know the gaps from the previous equation. So you try to fit as many as possible, making sure the minimum gap is as per the previous guideline. Then you take the second box and see it fits 3 cavities. Take the third box, you see it fits maybe 4 cavities. Then you calculate what is your metal to mold material ratio. Metal weight divided by mold material weight. Okay, and that ratio for ferrous castings should be in the range of 1:4 to 1:8. Which means if you are trying to pour 1 kg of casting, the mold material sand weight is typically 4 kgs. If you make it lower, let us say you make it 1:1 or 1:2, which means 1 kg casting poured into a 2 kg mold, you think you are being smart, but actually heat transfer is going to be bad and you might get a defective casting. On the other hand, if you take 1 kg casting and you are putting in a big mold box of 10 kg sand, you are unnecessarily recycling the sand. You are not being productive enough. So you have to balance both. The starting point is your minimum cavity gap. Take that as a minimum starting point, then take each box, and for each box calculate the maximum number of cavities, then finally calculate the metal to sand ratio, and a quick check will tell you whether you are utilizing the mold properly or not. Okay, that's the way to calculate that. So how do I now have some numbers to now see whether my mold design is good or bad? I have 3 numbers here. First one is fidelity. We say that what is my original designed volume or designed weight divided by my volume or weight of the cast part. Volume is a better indicator because weight can indicate also defects and all that. So we look at only design here, not the quality of manufacturing. So design weight by design volume by manufactured volume. We take to the power 4 because the ratio may be very small. It may be maybe 10% more, but if you say the design volume is 90 and then your actual volume is 100, so 90 by 100 to the power 4 gives you a bad number. So the worse the number, the better, more attention you will pay to that. So you make it to the power 4 because they are usually very close to each other. Next is your shape complexity, which you can measure using the previous way of doing that, or you can simply say n is the total number of mold elements, because total mold elements will be minimum how much? Investment casting, there is only one, there is nothing, there is no cope and drag, there is no, the core can be there, but you can make theoretically a single mold without any parting line. There is 1 by 1 which is 1, which is very nice. All these values closer to 1 is better. Okay, as you come down from 1, it is coming down from ideal to lower values. Then what about mold utilization? How do you calculate that? N is number of cavities, V is volume of each cavity, and V is volume of the total mold. So number of cavities into cavity volume divided by total mold volume, it gives you a mold material utilization. Okay. So to summarize this session, we looked at different transformations from part design to tooling design through draft, fillets, and various allowances. Okay. And after all the allowances, we find we have two more things, which is flash and mismatch, which makes life little more difficult. But finally, your idea is the difference between your design part and your final cast part should be minimum. That is what is your fidelity. And to improve productivity in the foundry, we make sure that the combination of the mold size and the number of cavities is optimized. Okay. So mold to metal ratio, metal to mold ratio should not be either too high nor too low. Both have to be optimized. Okay.